Good afternoon, this is Dr. Arberg. Today's presentation will be design and analysis of an actuator shaft. We'll look at the specification of the shaft, we'll design it in Inventor, we'll run finite element analysis with Inventor, we'll validate the result, we'll improve the result by adding fillets and changing the diameters. We'll size the bearings, estimate the cost, and compare the results with actual design. Linear stages are used extensively in automation. In particular, they are assembled in XYZ configuration, which is called Cartesian robot. They're also used for packaging, assembly, machining, testing, pick and place, and many other applications. For our exercise, we'll use a stage called HPLA. It's manufactured by Parker Hannifin, which is a leader in the position automation business. And the reason why we choose it is because it has the highest load thrust force on the order of half a ton, and it has a moment carrying capacity of 58 Newton meter, which is very high. We'll start by taking a look at the general outline of the HPLA 180. We see from it the general dimensions for our exercise. We'll start by conceptualizing our design. We have over here the shaft, and it is mounted on its two sides with two bearings. The values over here are taken roughly from HPLA 180, but absolutely had nothing to do with the Parker design. It's just for experimentation only. And over here we take the design objectives from the HPLA specifications with the maximum load, the maximum torque, and the sizes of the stage. We will choose randomly a safety factor of 3 for our design. We'll continue by making an outline drawing for the shaft with the estimated dimensions, and we select a design objective since we understand that the belt-driven stage has a continuous thrust force, but the bearing and the shaft are rotating. Therefore, we expect the failure mode to be fatigue. We look at the fatigue limit for steel, and we see that from the open source literature, as over here it's by reddit.com, at 300 megapascal. We'll have a safety factor of 3, therefore our target maximum stress of the shaft is 100 megapascal. We'll start with a sensitivity analysis to the various loads. We have a torsional load, and we apply it. We see that the result is 209 megapascal. We observe that there is stress concentration at the step, and we conclude that we need to apply some chamfer for stress relief. We also check the sensitivity to bending load, and we see that the bending load is substantially higher, 1579 megapascal, and we also see stress concentration at the largest step. We conclude that we would also need to add a chamfer over here. We look at the deflection of the bending force, and we see that the result is 188 microns. And we conclude that we would need to also increase the diameter of the shaft in order to substantially reduce the deflection. At this point, we like to validate the analysis and make sure that we're heading in the right direction. So we look at the open literature. This is from MIT, Alexander Slocum. We have here a consolidated formulation for stresses and stress concentrations for torsion. We plug in our values into these equations, and we come up with an estimated stress of 87 megapascal. With that stress concentration, we had 200 megapascal with stress concentration. Therefore, we estimate that if we would like to bring this value to the desired value, if we would increase the diameter to 18 millimeter, we see over here in Excel spreadsheet that the megapascal will reduce to 50. We check the results and we increase the diameter over here to 18, and we see that indeed the values over here, it's mostly blue and light blue, which is within 50 and 100 megapascal as expected. Over here we have at the key, we still have a stress concentration, but we'll take a look at this later. We then come in to do the bending analysis validation. If we plug into the equation, we see that we should expect 590. However, we receive 3 times a higher value. And we go through a similar exercise and find out that if we increase the size of the larger side, diameter where the bearing seat is to 36 millimeter, then we'll end up where we would like to be, around 100 megapascal. Then we also look at the validation to axial load, but since we don't have axial load, we need not do this analysis simply because it's not applicable to this case. The next step is to do some improvement of the design by iteration. So we like to apply the full load and see the effect on the design changes, where design changes is increasing the diameters to 42, 36, 18, adding some fillets, and then we see the result is still twice as much as we want to be. We observe stress concentration at the minor diameter fillet, and then we conclude that we need to increase that size. We observe the effect of increased fillet size, and we see that the change was not large, only reduced by 20 megapascal. Therefore, we conclude that we need to also start looking at increasing the diameter of the input shaft. Increasing the diameter to 32 millimeters reduce the maximum stress to 60 megapascal, and this is where we like to be. In other words, we meet the objective. We also like to take a look at the deflection, and we see that the deflection dropped to 20, an order of magnitude to 20 microns. To take a look at the implication of that 20 microns, we consider the stiffness. We know that we push in the shaft at the center with approximately 5,500 newtons, and we deflected 20 microns. Therefore, the stiffness is 272 newton microns. This is considered satisfactory. We know as a reference that the typical linear bearing stiffness is 100 newton per micron. Typical frame stiffness is 50 newton per micron. Typical stage, complete stage, is 10 newton per micron. And if we take an articulated robot and extend its arm 1 meter long, then the stiffness is only 1 newton per micron. The number over here is therefore considered to be satisfactory. We can then summarize the results of the design with the improved parameters. The shaft weight is 2 kilograms, and over here we see a summary of all the results. The von Mises stress is 60 megapascal. The deflection is 20 microns, and we also see here the reaction at the bearing. Now we can use the reaction at the bearing to size the bearing with Inventor. and we have an objective of typical 100,000 hours for bearing life in automation. We find a bearing that meets the criteria, and you see that everything looks proportionally reasonable. And we can also estimate the bearing costs by going to the internet and looking at the bearing specification. We find out in this case that it's about $120 per bearing. We can also estimate the shaft cost, material costs using online sizing tools is about $10. And then we have another $55 for machining costs with a total of $64 per shaft. Finally, what we like to do is a sanity check and see if the numbers that we came up with in our exercise are anywhere close to what the HPLA is actually using. And from some information available in Parker-Hannifin bushels, we see that the HPLA 180 has a maximum shaft diameter of 40 millimeter. The drive shaft diameter is 32 millimeter, and the distance in between the bearing centers is 93. Compared to what we obtained in our analysis was that the maximum shaft diameter is 42, the drive shaft diameter is 32, and the distance between the bearing centers is 170. Using the tools which are readily available by the manufacturers, this is an example of Parker-Hannifin sizing tools. We could go online, click this link, and then it will lead us to a configurator where we can choose all the parameters for the stage and come up with the results that will do the job. This concludes our presentations. What we see is that finite element analysis does not stand on its own. It actually working very closely with the design objectives, and we have to make sure that along the way we continuously go through checkups to make sure that the results that we obtain lead us in the right direction. Thank you.